Greetings to all my tech heads out there in the KevTechify Nation, and if you're new here, welcome. In this episode, we're going to look at IPsec. We'll be discussing IPsec concepts, IPsec technologies, IPsec protocol encapsulation, confidentiality, integrity, authentication, secure exchange with Diffie-Hellman, and finally, we'll look at IPsec transport and tunnel modes. This episode is part of my series on network security for the CCNA. I'm Kevin here at KevTechify. Let's get this adventure started. Internet Protocol Security, or IPsec. If we start with its history, we can see that the internet was not designed for security in mind. So the internet was not designed for security in mind. At that time, it was a private controlled environment. It wasn't a giant public internetwork of things that it is today. TCP/IP wasn't designed with embedded security as a foremost concern, because at that time it wasn't envisioned in what as to it would become. Security, when it was implemented at higher levels, like SSL and TLS for HTTP and FTP. That gives us our HTTPS and our secure FTP, or also SSH, our secure shell for remote command line. But what about the other applications that needed to be secured or needed security? IPsec was designed to solve this problem, to implement security for IPv4 and IPv6 at the internet layer. What this does then is it secures all the upper layers in the OSI model. IPsec provides us with some of the basic things that are needed in security. The first one here is authentication. Authentication for data origin, being able to authenticate that your data came from where you think it came from. It also gives us integrity, that it was not changed in route, and it also gives us protection against replay attacks if the information or data was intercepted, like in a man-in-the-middle attack. IPsec also provides encryption for data confidentiality, for keeping our data private, as well as authentication with integrity checks and protection against replay attacks. ESP, or encapsulating security payload, can provide us with those things. That is also part of IPsec. IPsec also provides us with negotiation of security associations and keys through Internet Security Association Key Map Protocol, also known as ISACAMP, Internet Key Exchange, known as IKE, and Diffie-Hellman. IPsec has two modes, transparent mode and tunnel mode. Tunnel mode is what is used for VPN tunnels. IPsec can be implemented in the kernel of the operating system, or it could be added to the stack. This is the more typical way, the adding to the stack. You have the application layer, and so right here we're talking about the application layer, which is in software. So it's done in software. Then at the transport layer here, this is where we have TCP. This is also done in software. And TCP, we can also put UDP into the same category. The internet layer, or IP, right here, this also exists in software. IPsec is added at the internet or IP layer. So we add an IPsec, we add that in at this layer here. And this is also implemented in software. So all of these right here, application layer, transport layer, IP layer with IPsec, this is all done in software. But in comparison, the network access layer here, this is where we have the data link and the physical layer, and this is done in hardware. So the network access layer, and once again for the OSI model, it's the data link layer and the physical layer. This is implemented in hardware. When we use IPsec and have it added to the stack in the end device, it's called a bump in the stack. So where it's added to the end device, so a laptop, a PC, That is called a bump in the stack. When we add IPsec in on a networking device, on a VPN gateway, on your edge router, that is called, so we're down here on a network device, that is called a bump in the wire. So here we have all the protocols that are used in IPsec. IPsec is more of a suite or a framework of protocols and security technologies than anything else. Let's take a look at the main protocols. The main protocols here for IPsec are Authentication Header, Encapsulating Security Payload, Security Association, and Internet Key Exchange. The Authentication Header, also known as AH here, is more of a header than a standalone protocol. And it's waning in popularity because though it can provide the ability to authenticate data origin, that the data is from where you think it's from, as well as integrity of the data, that it wasn't changed en route, it doesn't provide confidentiality or encryption. Authentication header also doesn't work with NAT firewalls. It can't traverse network address translation. Encapsulating security payload, or ESP, does provide confidentiality through encryption, and it can provide some of the same authentication methods like integrity checks. And what this does is this enables you to verify the integrity of the data. ESP is more popular because of these reasons. Then we have security associations, also known as SA. And these are used to set up basically a contract or a recipe for how security is going to be handled from each device or from each end of the IPsec connection or tunnel. Now, security associations are built on IKE, or the Internet Key Exchange. And IKE uses the policies laid out in the Internet Security Association Key Management Protocol, also known as ISACAMP, to set up these security associations. Now, there are two phases in IPsec. There's the phase 1 security association and the phase 2 security association. Phase 1 security association is used for management. So down here, phase 1 is used for management. And phase 2 is used for data, transferring our data. Phase 1 creates the policy set. Phase 2 creates the transform set. There's a single policy set used for management in phase 1, and there are two, one inbound, one outbound transform sets used for data. All these things that are set up in these two phases in the security associations are basically all of the security methods we are going to be using. In phase 1, what is negotiated is the IP policy set. And there we lay out the encryption that's going to be used. Let's say it's triple DES or AES, so 3 times the data encryption standard or advanced encryption standard. The hashing that will be used, like message digest 5 or the secure hash algorithm or the hashed method authentication code, or HMAC, which is a keyed hash. The method of authentication, each one of the IPsec tunnel using X509 or pre-shared keys or public keys, or the Diffie-Hellman group. Which Diffie-Hellman group are we going to use? Phase 2 negotiates the transform set. This is used to secure the data. Now, the transform set, we set up the encryption that's going to be used. Let's say we're going to be using the encryption security payload with advanced encryption standard and a 256-bit key. This is also known as ESP with AES. And then the hashing that we're going to use for integrity check, let's say we're going to use the encrypting security payload with secure hash algorithm with a keyed hash using the hash message authentication code, or HMAC. Those are the basic protocols, or the suite of protocols, that we'll see in IPsec. I hope you're liking this episode on an IPsec overview. If you have the time, please leave a comment and let me know what you think about IPsec. You can also visit my website at KevTechify.com for all of my details and how to get these episodes in video and podcast form. Using the IPsec framework, IPsec provides essential security functions. So we have our IPsec protocol here. The first function it provides here is confidentiality. IPsec uses encryption algorithms to prevent cyber criminals from reading the packet contents. Then we have integrity. IPsec uses hashing algorithms to ensure that packets have not been altered between source and destination. Then we have origin authentication. IPsec uses IKE, the Internet Key Exchange Protocol, to authenticate source and destination. Methods of authentication including using pre-shared keys, which are typically referred to as passwords, digital certificates, or RSA certificates. And then finally, we have the Diffie-Hellman. And this is used for the secure key exchange, typically using various groups of Diffie-Hellman algorithms. There are several functions of the IPsec security protocol. First one here we're going to look at is just the IPsec protocol in general. The choices for IPsec protocol include authentication header, which is typically referred to as AH, or encapsulation security protocol, which is ESP. Authentication header authenticates the layer 3 packet. ESP encrypts the layer 3 packet. Note, ESP and AH is rarely used, as this is a combination that will result in not successfully going through network address translation. Then we have confidentiality. Encryption ensures confidentiality of the layer 3 packet. Choices include data encryption standard, which is known as DES. We have triple DES, which is 3 times that DES, that data encryption standard, so it encrypts it 3 times. Then we have AES, which is advanced encryption standard. Or finally, we have software optimized encryption algorithm, also known as SEAL. We also have integrity. This ensures that data arrives unchanged at the destination using a hash algorithm, something like message data 5, so MD5, or SHA, secure hash algorithm. Then we have authentication. IPsec uses Internet Key Exchange, also known as IKE or IKE, to authenticate users and devices that carry out communication independently. IKE uses several types of authentication, including usernames and passwords, one-time passwords, biometrics, pre-shared keys, and digital certificates using the Rivest-Shamir-Adelman or RSA algorithm. And then finally, we have Diffie-Hellman. IPsec uses Diffie-Hellman algorithm to provide the public key exchange method for 2 peers to establish a shared secret key. There are several different groups to choose from, including DH 14, 15, 16, and Diffie-Hellman 19, 20, 21, and 24. Diffie-Hellman 1, 2, and 5 are no longer recommended because they are considered insecure. Choosing the IPsec protocol encapsulation is the first building block of the framework. IPsec encapsulates either using the authentication header, AH, or encapsulation security protocol, ESP. The choice of AH or ESP establishes which other building blocks are available. AH is appropriate only when confidentiality is not required or permitted. ESP provides both confidentiality and authentication. Confidentiality is achieved by encrypting the data. The degree of confidentiality depends on the encryption algorithm and the length of the key used in that encryption algorithm. The shorter the key, the easier it is to break. DES uses a 56-bit key and should be avoided. So 56-bit key, very short. You should avoid using DES at all possible. Triple DES uses 3 times that 56-bit key, so it encrypts it 3 times. AES offers 3 different key lengths: 128-bit, 192 bits, and 256 bits. Steal is a stream cipher encrypting data continuously. It uses a 160-bit key. Data integrity means that the data that is received is exactly the same as was sent. MD5 uses a 128-bit key. It's a shared key, and the variable length message and the 128-bit shared secret key are combined and run through HMAC MD5 hash algorithm, producing a 128-bit hash. The secure hash algorithm, also known as SHA, that uses a 160-bit secret key. The variable length message and the 160-bit shared secret key are combined and run through HMAC SHA-1 algorithm, producing that 160-bit hash. When conducting business long distance, the device on the other end of the VPN tunnel must be authenticated before the communication path is considered secure. We're going to look at the pre-shared key first. So we're looking at pre-shared key authentication. A pre-shared key value is entered into each peer manually. So here we have the authentication key. Somebody has to go and manually enter it in this local device. Somebody has to go and enter it in at that remote device. That pre-shared key is combined with other information to form our authentication key. For Ribus-Shamir-Edelman authentication, also known as RSA authentication, it uses digital certificates to authenticate the peers. Encryption algorithms require a symmetric shared key to perform encryption and decryption. How do the encrypting and decrypting devices get that shared key? The easiest key exchange method is to use a public key exchange method, something like the Diffie-Hellman method. Diffie-Hellman provides a way for two peers to establish a shared secret key that only they know, even though they are communicating over an insecure channel. Variations of Diffie-Hellman key exchange are specified as Diffie-Hellman groups. The Diffie-Hellman group you choose must be strong enough or have enough bits to protect the IPsec keys during negotiation. In transport mode, there's only the single IP version 4 header, which isn't changed. Right here, we have our IPv4 header. We use protocol 50 to point to the fact that we are using ESP, the encapsulating security payload, and the encapsulating or the ESP header is then added. So protocol 50 points and says, hey, we're using ESP, let's add in our ESP header. There's also an ESP trailer. Way over here, we have our ESP trailer. And that trailer tells us that the next header to look for is the TCP header in the encrypted IP data. And so this says, okay, here's the next header we're looking for. This next header is over here is our TCP header. So once this is decrypted, we'll have the TCP header next. In transparent mode, there's only a single IPv4 header, which isn't changed. So right here is our single IPv4 header. And we use protocol 50 of that IPv4 header to say we're going to use ESP, which is encapsulating security payload, and we add in an ESP header here. There's also an ESP trailer way down here at the end, and the ESP trailer tells us that the next header to look at is the TCP header in the encrypted data. So ESP trailer says, okay, now look at the next header, which is our TCP header right here. We're going to go ahead and look at that. So once this is decrypted, we'll have a TCP header next. Here's the encryption security payload or ESP authentication data. And this is used if the option is used with ESP, then we're going to also have authentication, meaning we're going to have an integrity check, or we're going to hash the entire fields, including the ESP header, all the way down to the ESP trailer. We're going to include all that into our hash, and we're going to hash all those fields, and that way we can verify that the integrity of the data, that it wasn't changed in transit. Let's compare transport mode from the previous slide to tunnel mode, which is used in virtual private tunnels. In this case, the entire original IPv4 packet is encapsulated and encrypted. Not only the IPv4 data with the TCP header and TCP data, including the application layer data, but the original IPv4 header is encrypted along with the ESP trailer. We encrypt everything from this right here all the way down to the end here. Notice that the ESP trailer says that the next field right here, that our ESP trailer here says the next field, and it'll point to the IPv4 header. That's what the 4 signifies. It points to the IPv4 header. There's an IP address, and there's a new outer public IP address over here. So now we have a new IPv4 header with a new IPv4 address. That new IPv4 address points to the fact that we're using protocol 50. So the IPv4 header here says we're using protocol 50, that we're using ESP. Let's add in our ESP header here. And we're also saying we add in the ESP trailer. With the ESP header and ESP trailer, we can use the ESP authentication data here if we decide to have integrity checks or authenticated information through hashing. This type of packet, you would see that the encapsulated security payload, or ESP, or virtual private network tunnel, with the original IP address and the new public IP outer address. So once again, this is the new address. We get this basically because we're connected to our VPN. Here we have the original IPv4 address. The new address allows us to go across the internet, across a public network. The original is for our local area network, internal to our company. It was my pleasure to provide you with this wonderful episode on an IPsec overview. If you like this episode and you got value out of it, and of course, depending upon what platform you're using, please click that like button, give a 5-star rating, leave a comment. This all helps me bring you more great content. Please take a minute to subscribe to my channel. All my socials and contact information are on my website, KevTechify.com. There you can find out how to get all these episodes in video and podcast form. In the upper right is my playlist for my series on network security for the CCNA. In the bottom right is one of my favorite videos that I picked just for you. Thank you so much for watching this episode of my series on network security for the CCNA. I'm Kevin. This is KevTechify. I'll see you next time for another great adventure.